Right, this is session number 4, water distribution.
Correct. Let's start. And hopefully you can see this all right. Does that work okay?
Yeah, correct.
Okay. Yeah. All right, well, let's get going. Good, well, I keep wanting to say good morning, but it's not. It's good mid-afternoon to everyone. So today, I understand you went through some of the fundamentals of distribution, treatment, water treatment. Even though it's a distribution exam, there are questions that will come up on cert exams with that. And some of you may actually not work in this area of a distribution system, but it's a good background to have. There are usually a couple of questions on the cert exams to do with the hydrological cycle and water in its different states, be it a solid, a liquid, or a vapor, and of course how it affects our water supplies. And then we'll talk a little bit about, I have a video as well on that, so hopefully that'll share okay, a short video. Then we'll talk a little bit about the difference between groundwater supplies and surface water supplies. And I'm actually not aware, depending on which system you are working in, whether they are surface water, lakes and reservoirs, streams and creeks, or if it's a well-based groundwater system. So we're going to talk about both as the distribution certification process covers off both, and the different requirements for storing the water and also moving that water from its primary location. We're going to talk a little bit about, primary storage, which is raw water, versus finished water storage, which is treated water moving into a steel tank or a concrete tank, or some of the older tanks were wood stave. Or I've seen some small water systems in BC that actually use children's swimming pools and hot tubs as their reservoir, their source of water, because, when you're thinking of pumping from a source, you don't want that well or jet pump to be running all the time, so you pump into storage. And people have been very creative about using anything large, any large vessel as a storage vessel for finished water. The trick is, of course, to make sure that it's safe, that it's disinfected and fit for consumption, and also that it provides the supply that you need, whether it's for domestic or outside use, or potentially for fire protection. So we'll cover that off and then look at parts of a well, how a well operates, and some of the tricks around maintaining that. And again, one eye always on your exam. And as I mentioned to Ignatius, actually, maybe what I'll do is, I'll do it now. I'll send you the file if I can. And try and get you the, I'll share. Actually, I will do that in a minute. Let's hold off on that, because I don't want to be sharing that one. So what we'll do is we'll start talking about the hydrologic cycle. And as I say, I've got a video that I want to show you. So some of you may be aware of the term, but basically sometimes it's called the water cycle. And really it's about understanding how water gets to be in a position where we can supply water to our communities. And as you know, I mean, basically water is not, fresh water isn't very evenly distributed around the planet. These are the 7 stages. Sometimes on the exam, they'll ask you to define the movement of water from its liquid form into the atmosphere to a vapor. either through evaporation or evapotranspiration or just transpiration itself. So those are the two terms to be familiar with. When water moves through the action of heat, the sun's rays, water moves from a liquid to a vapor. And of course, in the atmosphere, eventually it will condense through condensation and fall to the earth again, either in the form of snow, sleet, hail, or rain. So either in a solid or in a liquid state. When it hits the ground, it's the surface of the earth, it then either can act as runoff through snowmelt or direct from impact onto the earth, runoff on the surface into a source, or it can infiltrate or percolate into the soil and then recharge our groundwater aquifers. So really this cycle and these stages of water are, of course, always happening. You know, it's either winter in half the world, the northern hemisphere, or vice versa. So the process of water falling back to Earth could be in a solid. So the northern hemisphere right now is basically in winter, so that's what we're seeing in a lot of places. And again, we don't get very even distribution of water, fresh water, in our system. So what we're looking at is, you know, it's a cycle, and the important points to remember. It doesn't have a beginning or an end. It is basically as they say, a perennial in motion series of chemical changes to water, fresh water in our system. And of course, it can take water from saltwater bodies as well and put it back into the atmosphere, either through direct evaporation or through wind action across the top of the bodies of water, and then eventually back to Earth again. So be familiar with the terms, you know, the precipitation, transpiration, infiltration, and so on. Basic facts: 73% of the Earth's surface is water, but less than 3% of that is fresh water. And of course, that's a fixed amount. And as you know, and are probably keenly aware of in some of your water systems, not necessarily fairly or equitably distributed. So, you know, looking at it visually, fresh water is only 3% out of the entire water supply on the planet. Of that 3%, 79%, and declining actually, is locked up, frozen in glaciers. So a lot of that is inaccessible to freshwater supply or for use for consumption. Of that remaining 20%, basically, is groundwater and freshwater. Actually, there's a math error in here. And then out of the freshwater supply, only 1% of accessible surface water is fresh water. The rest of it is oceans. And of that, where is the rest of it reside? 52% in lakes, within organisms themselves, 1%, and that includes us, rivers, streams, and as water vapor. In North America, and it'd be interesting to compare that with your associations to see where consumption is. But in BC, the province I live, has one of the highest per capita water uses per person of over 375. It's actually gone down. About 5 years ago, it was well over 400 liters per person every day. Now, they're not drinking that much water, but you know, when you look and break down where water use is happening in BC, of course, 40% of water that comes through a water system, treated water that goes through a water system in BC, is used outdoors. So for residential communities, that's irrigation, gardening, growing vegetables and flowers, and washing cars and boats and things like that. But it's a high usage. Now, you know, the interesting thing in this part of the world, we average for cost, it's about $3 a cubic meter. So that's 1,000 liters of water for $3. You see the people in the picture are drinking out of a plastic water bottle, and probably that's $1, for a liter bottle. It might even be more because a lot of the bottles are 750 milliliters. So to buy that much water at a store, you're looking at $1,000 Canadian dollars, as opposed to $3 Canadian dollars to have that same volume of water, safe, disinfected, treated water, piped into your house. So I'm not sure, what your costs are, retail or wholesale. If you're aware, I mean, that's, one of the biggest selling points for a public water utility is that it provides safe drinking water, and usually aesthetically quite pleasing, for pennies on the dollar. And again, we're going to talk a little bit about both surface water and groundwater. Surface water consisting of lakes, rivers, any open body of water that then can be subject to evaporation, but is then replenished through the hydrologic cycle through a series of rain and or precip. And I think this is a good time to show, I've got a short video on the hydrological cycle. So let's try and show you that. Let's just tee it up, make sure it's ready to go. Yeah, this is from one of the environmental sciences groups. So let's try that, and hopefully it will holler or send me something through chat if you can't hear this properly.
Hi, it's Mr. Anderson, and this is Environmental Science Video 5. It's on water resources. Our body is filled with over 60% water, and this doesn't seem like a big deal because the Earth is covered with over 70% water. The problem with that is that most of that is seawater that we can't use. And the fresh water that remains, most of it's going to be frozen in ice caps and glaciers. And so the percent that is really fresh water on the surface is a small percent of the water on our planet, and it's finite. The amount of water we have on our planet has never changed. Now, as the sun provides energy to the earth, the water will move around through the hydrologic or the water cycle, but we have a finite amount of water, and most of it is going to be seawater. We have a little bit of fresh water. The seawater moves around through ocean currents. The fresh water could be divided into groundwater, water underneath the surface, and then surface water, which is on the surface. Now, we need that water. We need it domestically in the home to take a shower or to drink, but we also need it in industry to make our goods, and most of it actually goes to agriculture to make the food that we eat. The problem with water on our planet is that it's unevenly distributed. In some areas there's lots of water, in some areas, however, there's going to be scarcity. And so humans have had to learn how to store water, move it around, and in the future we may have to desalinate some of that seawater so that we can use it as fresh water. Now, where is that groundwater stored? It's underneath the ground in aquifers that we can deplete. What about the surface water? Well, it can be stored in reservoirs that occur naturally or ones that are created as we produce dams. And then we can move it around through aqueducts and even to the plant itself through irrigation. But we have a finite amount, and so conservation is incredibly important, and economics have contributed to water loss and could help us to actually solve this water conservation problem. And so the hydrologic cycle works like this. Anywhere there's water on the surface, we can have evaporation. That gets cooled and eventually leads to condensation and precipitation. Once it's on the surface, we call that surface water. It's running over the surface. That could be lakes and swamps and rivers. After we have that water hit the ground, it can, however, be infiltrated into the soil and the ground itself. To give you an example of that, imagine I've got a beaker here. Is it full? Well, maybe full of air. If I put marbles in it, is it full? No, you can still see there's spaces in it. What if I fill it up with sand? Is it full? No, there's still spaces in there. If I fill it up with water, now we're starting to fill up that beaker. And that's what infiltration is. As the water flows down into the soil, we call that now groundwater. Let's say it's not filling that whole beaker, it's right here. That point at which we have saturation in the groundwater is called the water table. Most of our planet is covered with water. Unfortunately, it's seawater. It has salt dissolved in it. If you drink it, you'll die. If we put it on our fields, the crops are going to die. Now, it moves around using currents. We talked about that in the last video on the atmosphere. It sells in the atmosphere and the Coriolis effect. So we have these general trends in circulation, but also salinity affects it. And so if we look at an area right here, it's a high salt concentration because we have a lot of evaporation. But up here, we have a lot of melting of that glacial ice, and so we're going to have a low salt concentration. And so the salt concentration and differences in heat create these thermohaline circulation that really make that whole ocean on our planet one system. Now, if we look at fresh water, it can be divided into water that is above the surface, we call that surface water, and then groundwater. But what's interesting is if we look to the sides of that stream, you can see the water table in the groundwater. And so if you dig a hole right here, it's just going to fill in with water because of all that groundwater around it. Now, this is an aquifer. It's storage of that water in the groundwater. We call this unconfined aquifer because the water can move between the surface and the aquifer itself.
So this is on every certification exam, that to be able to define an unconfined aquifer as opposed to an aquifer that's confined by the soil, the composition of the soil. But it's a good cross-section of seeing where the water table or that top water level is in our groundwater supply and how it can turn into surface water based on the contours and configurations and elevation changes.
If I were to dig down a little bit, we could find what's called a confined aquifer, and that's going to be stuck between this impermeable rock down here and above it. Now, let's say we want to get to that groundwater on the surface. If we want some of the surface water, we simply pump it out of the stream, but if we want to get out of that groundwater, we could dig a well. Now the water, we could either pump out the water, or sometimes we'll have what's called an artesian well, where there's either enough gravity above it or enough pressure in the groundwater so it actually comes out. But as we use that well, just like using a stream, the water table is going to drop, and so we're going to start to deplete that aquifer. Now, an important term in filling an aquifer is something called recharge. So as we get water and infiltration, we're going to fill up that aquifer, but if the outputs, in other words, if we pull out more water than we're putting in, we're going to deplete the aquifer. And what are we using all this fresh water for? Well, if we break it out using a pie chart, most of it is actually for agriculture, the growing of our food. We use some of it for industry, and then some of it domestically in the house. The problem, again, is that it's unevenly distributed on our planet. Brazil's going to have plenty of water, but if we look in the desert southwest of the US or in the Sahara, there's not going to be any water right there. And so what have humans done? We've started to store water. So reservoirs are an example of that. A big example would be the Three Gorges Dam that was built in China, finished in 2006. And so this is what that river, the Yangtze River, looked like before they built the dam. And then they built the dam, it finished in 2006. You can see what it looks like then. So we're storing the water behind the dam. What's nice about that? Now we have water that we can use at will. We also can get energy from it as we run that water through a generator. We can control flooding downstream, and also we can use that for irrigation or the Three Gorges Dam they're using to increase shipping on the Yangtze River. So it sounds great. What's the problem? Well, there's going to be destruction wherever that water went. So we're decreasing 20% of the forest in this Yangtze River. We're displacing over 1 million people that used to live there. We also have evaporation of the water off the surface, and then we're going to have nutrients that start to deposit there that would have normally moved their way down the river, and that's going to disrupt wildlife. And so fish obviously can't spawn, move up and down in the stream, but it's also going to change the temperature of the water. Example, there's a freshwater dolphin that went extinct in the Yangtze River, and the Three Gorges Dam may have contributed to that. We can also store it underground. That's naturally stored in what are called aquifers. One of the largest ones on the planet is the Ogallala Aquifer. It's going to be found in the Midwest, and so here it is in Nebraska, but it goes all the way down to Texas and up into South Dakota. It's a huge aquifer. So if we look at the amount of water stored underground, it's over 1,000 feet of infiltrated, saturated water underneath the ground that we can use. And you can see right here, there's tons of irrigation going on. This is in Kansas. They're using center pivot irrigation so they can grow their crops. Seems great, but what happens again is that we can deplete that. So if we look at This is during a 10 or a 15-year period of time. There's an increase in the aquifer in certain areas, but most of the time we're seeing depletion. And sometimes that aquifer has kind of disappeared. And a lot of scientists think in the next 100 years, the Ogallala aquifer is just going to disappear. Why is that a problem? It could take another 6,000 years to fill it up again through recharge, natural recharge. Now we also have to move water around. So looking to California is a great example of that. So if we look in California, they need a lot of water in the Central Valley and then in the south, Los Angeles and San Diego. So they built this huge system where they can move water where it is in the mountains, and they can move it through these aqueducts to where it's needed. Now you can see that's controversial. So people in this area are saying you're depleting our rivers. In this area, we're saying we have more population, we're growing your food, so we need more of that water. And this conversation becomes more heightened when we move into drought, and California is in an awful drought right now. Drought occurs when you receive way less than the normal amount of water. And so as we use that for agriculture, irrigation movement is super important. So how do we move the water actually to the plant? The easiest way to do that is using furrow irrigation. You can see it's easy, you just dig a trench. What's the problem? We have efficiency rates of around 60%. What's that? It's how much of the water is actually going to the plant without being evaporated and infiltrated into the soil. So we could move to flood irrigation, higher efficiency, but it's going to damage the plant a lot of the time. We could move towards a spray irrigation, high efficiency, but what are we doing? You can see we're adding equipment. This is a center pivot, so that costs money. Or we could move to drip irrigation. You can see it's going to be 95% efficient, but it's going to cost the farmer a lot more money to do that kinds of irrigation. As we move into drought situations, desalination becomes an option. We can remove the water from seawater. One way to do this is through distillation. What you do is you heat up the water and it evaporates. It's kind of like the hydrologic cycle. You then cool it down, usually through pipes, and what you do is you remove the water. What's the problem? Costs a huge amount of money. We could also do that through reverse osmosis. This is a reverse osmosis plant over on the side. What you do is you put a membrane right here, and then we squeeze the water, and as you squeeze the water, you move the water through, but you leave the salts behind. Now we have fresh water. What's the problem? Costs a lot of money. About 1% of the people on our planet are using water that's created through desalination, but by 2025 we should have 14% of the people on our planet in water scarcity, and so desalination may be an issue. Now how did we get to this problem? It seems like we have an unlimited amount of water, and remember our model that the earth provides the life support for society and the economy on the inside, and so the economy got us to this point. The decisions that we as governments made got us to this point. Where's the big mistake we made? Well, water doesn't cost enough. It's low-cost water. In other words, governments are subsidizing the cost of water, so farmers and industry and you are not really paying the amount that water costs. And as a result, you're not going to conserve it because it's just pennies on the gallon. It's incredibly cheap. And so how could we solve this problem? People might not like it, but if we increase the price of water, people are going to start to conserve. And we can also use incentives. In other words, we can pay people to use, pay farmers, for example, to use irrigation that's going to be more efficient or to conserve water. That's another way that economics can start to solve this problem of water conservation. And so did you learn the following? I would pause the video at this point and try to fill in all the blanks. But let me do that for you. Remember, the water resources move through the hydrologic cycle. We've got seawater, we've got fresh water. Ocean circulation and desalination could help us solve this problem. The fresh water can be groundwater or surface water. We use it for domestic industry and agriculture would be what's here. We can store the surface water through reservoirs. Aquifers is groundwater. And then we're going to use aqueducts and irrigation to help us move that water around. But again, conservation is incredibly important. Economics are going to drive that. And I hope that was helpful.
All right. So several of the points that we talked about already in terms of both the hydrologic cycle and how we move the limited resources we have. And it's interesting because, you know, California the last couple of years kind of came out of a drought for a while, but in the big picture, of course, the issue is that they've had to change to some different modes of growing crops because some of the crops, especially almonds and avocados, are very water intensive. So they've changed that. And it's one thing for a government to say, we're going to raise your water rates. In BC, we had a report done by the BC Water and Waste Association a little while ago on the actual cost. Are water utilities charging enough to actually pay for the infrastructure? So never mind the water itself, the product. We're just talking about packaging. And the answer is no. So we're not even charging people enough to upgrade the infrastructure. And you may have your utilities in similar situations where pipe is aging, pumps, motors, valves need replacement, and there isn't sufficient budget for that. So, of course, metering helps. And we're going to talk later in the program about how we use water meters to ensure that, you know, the utility is recovering adequately for the water that actually goes through the meter. But most utilities in the world don't actually charge for the water. What you're paying for as the meter spins is the cost to deliver the water, to treat the water, to build the storage facilities if it's well run. And of course, you know, a lot of utilities in North America and around the world, in your part of the world, Africa, South Asia, are dealing with the fact that they treat, say, for every 100 liters of treated water that the treatment plant produces, or the well, only 50 liters makes it to the customer. So then it's almost doesn't matter what the source was, whether it was surface water or groundwater. If half of the product doesn't make it to the customer because of leaky pipes or poor storage facility condition or inefficient pumps, not only is the utility losing money, it's not going to recover the cost of delivering that water. And the most important part of all of this is the resources lost. Treated water goes back to ground and then must be treated again before it can be put back into the system and delivered. So some real challenges for water systems around dealing with water sources and supplies. And of course, the sort of the accountability around, well, first of all, we may not be paying enough as it is to supply, you know, to pay for the utilities needs, i.e. the capital expenditures, the annual maintenance, and the staffing levels. Not only that, we're actually not charging for the water itself. And the example I gave at the beginning about the price of a liter of bottled water, which in many cases, the larger companies just use municipal water. It runs through a meter in their plant, they put it in a bottle, it's been treated by the municipality, they may treat it again or distill it in ways to create their own proprietary formula, and then they sell it. So that's a different issue, but it all comes back to, you know, do we have sufficient supply, whether it's groundwater or surface water? Are we providing enough water in our sources that we can then do what our community is asking of? So let's go back to the PowerPoint. Okay, so surface water, groundwater. The video is actually really good at showing that cross-section animation of basically, I really like that example of taking a beaker and filling it full of marbles, filling it full of sand, and then it's not full until you add water. And you know, when you imagine an aquifer or groundwater supply, it's not a hollow space underground where all this water is sitting there like an underground swimming pool. It's actually just contained and locked up in between the particles of sand or clay or bedrock. And of course, it's those pores in between the different materials that fill with water. And, you know, with the California situation, as an example, you know, the wells have had to go deeper and deeper because the aquifers are depleted. They're taking more out than can be recharged or replenished through the hydrologic cycle, that they're actually tapping now into water that they think might be there have been there for over 1 million years. So just as in the Guala example, takes 6,000 years to recharge it. Well, you know, we don't have 6,000 years, right? We need the water now for our various, what our community is asking us to supply water for. Other sources, he mentioned desalination. Israel uses a lot of desalination. It's still not the primary source. Military groups, engineering corps in Afghanistan and other places have desalination plants as a quick supply of water, of clean water. Aesthetically, may not be the same as a surface or a groundwater supply, but it can be done. The question is, how much does it cost, and how do you build a plant large enough to build to supply that much water? Of course, reclaimed water, and it's quite, you're seeing more and more of what's called gray water, which can be simply used for irrigation. There are a lot of places where you'll see "do not drink the water," and it's typically on garden planted landscapes and so on. But it's basically been treated wastewater. And for so many communities, they have their primary surface water supply as a river that is downstream of some other communities' discharge for their wastewater plant. So the treatment part of it becomes really critical. So let's talk a little bit about collecting water for storage from a surface water supply. And there's an example of a steel water tank. And remember, you know, there were a couple of examples with the confined, unconfined aquifer, and the you will have to define in the first level exam what an artesian is. And it's basically groundwater that, because of the water table elevation, is actually creating enough pressure to actually push that water to the surface under pressure. This tank, remember in hydraulics, doesn't matter the shape or size of the vessel, it's the elevation of the column of water that creates the energy, right? So this tank is an example of one that has been built and configured of a particular height so that that top water level within there provides the necessary energy, right? The pressure to supply to the properties. It also has been built in size to provide sufficient quantity of water, which is really what you think of with storage. With surface runoff, you know, if we're collecting water for our system from the surface, then, you know, the things that engineers and system designers have to consider is, when does the water show up? How intense is it? And that intensity is how much water comes in that, say, 30-minute period of a storm. Precipitation happens for 30 minutes. And one of the interesting papers that I read about climate change in the Northern Hemisphere isn't so much that it's the temperatures changing that much, but it's the intensity of storms, either the intensity of drought or the intensity of rainfall events. So a 30-minute storm that might produce 5 millimeters of rain, the concern is that it is now producing 50 millimeters. So great, you've got lots of water, but if it all comes at once, a lot of times it overloads our drainage systems. It can cause erosion and sediment deposits in either surface water supplies or in lakes and plug up our intake systems. But it can also destroy property, vegetation, agriculture, and so on. So intensity becomes a huge calculation and consideration. The duration is the other half of that. How much comes, but you know, how long are those rainfall events? The soil composition, you know, water coming in the form of precip out of the sky, you know, condensing in the sky and then dropping. If it's hitting asphalt, it's going to move very quickly. But if it's hitting bare ground, it can take some of that sediment with it, you know, and create real issues around erosion. Obviously, the slope of the ground where that water hits becomes an issue. The steeper means water moves faster. And that's not always a good thing. And with the changes in rainfall intensity and duration over the last 30 to 40 years, it changes then how systems get developed in terms of, are they oversized, undersized typically, and are they actually able to handle some of the changes in terms of of the actual surface water supplies, volume and composition, and man-made influences. So whether that's hard surfaces, actual building, roads, dams, that sort of thing. So we take runoff and move it to where we want it. If we can, use surface water supplies in our systems. So we can either have natural streams or, as it was shown in that video, aqueducts, large scale ditches and channels that are open. And so as Dude said in the video, not necessarily the most efficient, because of course then you have evaporation and loss from those channels. But we can move large amounts of water. And if you look at that little graphic in there, if you imagine that, you can see the red dotted line. So just imagine one drop of precipitation hitting the landscape. So when it hits the downward slope of a hill, it drains in towards the low point in that watershed or catchment area and becomes available to be used. But you can imagine, if you think about that drawing, if you move the little raindrop further and further up the hill, you're going to eventually hit that spot where the surface runoff runs the other way. So it may rain a lot there, but it's not going to run into your catchment. So it's then unavailable. And you see that lots of places where you have rain shadow, wet, dry sides of a valley or a region. And a lot of times the development and the agriculture happens on the wet side, because you cannot harness any of that water that's outside the watershed. Oh, and by the way, it just doesn't happen to fall there either. So that watershed, we can then actually calculate total flows through a year, a month, a season, based on historical records. How much water has landed in the watershed? How much have we actually produced, or we haven't, nature has produced and created for us to use. And we still have to treat it and disinfect it and do all those other things. But we can actually build out the system based on the known quantities within each watershed. And some cities have multiple watersheds. You see the city of Los Angeles basically takes multiple watersheds. There are a bunch of YouTube videos on the New York water system. Of course, New York is a big city, but it's also an old city. And from its origins of having basically an open lake in the center of Manhattan, the population is so large that miles and miles of pipeline have been installed and tunnels to pick up surface water from way up in the Catskill Mountains, miles and miles and miles away. You're in the country. And multiple watersheds to create the supply, the surface water supply, that is then tunneled, transmitted basically all the way into the city of New York, which is millions and millions of people now. So, as systems grow, they adapt to those environments. But it's also about knowing, well, where are the surface water supplies in the first place? So we can use the surface water either to feed natural lakes and ponds, or we build reservoirs. That example in the video of the Three Gorges in China was built, the dam was built to create what's called an impoundment area, but basically impounded water just means we've locked up a specific volume of water to supply whatever our needs are. In BC, there's a big dam being built up in the north called Site C, mostly for hydroelectric. But some of the concerns environmentally were, you build a dam on the river and you impound the water behind it, it's going to have an environmental impact. It's going to affect people's livelihoods if they fished or hunted in the area or lived in the area. Affects logging, affects all sorts of things. So usually dams are built with very careful consideration about what are the impacts going to be. A lot of water supplies, surface water supplies, are also what we call mixed use, that they may be a supply for people's drinking water, but they're also recreational. The biggest recreational lake in BC is a lake called Okanagan Lake, right in the middle of the province. Shouldn't say middle, but southern half of the middle of the province. And all of the communities ringing the lake use that surface water for their drinking water. They either take it from a creek on its way to the lake, or they take it right from an intake that they have built and stuck into the lake itself. But millions of tourists go there every summer to swim, to boat, camp, and so you've got, you know, the risk of either contamination or basically a competition of who gets priority. And surface water, you know, the old argument is that if you have a barrel full, you just think about this, you know, you're in a wild state, so you've got animals and people and birds, and, you know, lots of poop ends up in the water, so you got to treat it. But, you know, so a barrel full of sewage, and you put a glass of, or a teaspoon of drinking water into that barrel full of sewage, you have sewage. So you have a barrel full of treated drinking water, and you know, you do the reverse and you put just a teaspoon of sewage. What do you have? It's sewage, right? You've got to make sure that whatever your source of water is, that contamination risk has been mitigated. So where you have surface water that is shared in terms of its usage, and there's a huge economic driver for bringing people to those neighborhoods, those cities in the summer for recreational use. So no one wants to stop that. Well, okay, then it just means that your water system has to adjust to that. Whereas if you come to the coast of BC, both on Vancouver Island where I live, or in the area of Vancouver itself, which is 2.5 million people, those are surface water supplies, natural lakes that have been impounded to create storage. Those are closed watersheds, so there is no recreational use. So you don't have people swimming or boating or fishing on those lakes. Now, there's still wildlife. There's still heavy rain that sometimes brings turbidity into those water supplies, but the risks have been mitigated. So you still treat the water, but you're not competing with those other types of uses and demands on the water supply. Huge. And those watersheds were closed 1920, so 100 years ago. In Victoria, they even closed it to, there was logging in there up until the 1960s. So recognizing that this is a water supply first and foremost. Whereas other impounded natural lakes or ponds or streams have recognized that, you know, we have to realize that there are other uses happening and taking place. Here's an example of a reservoir that is a recreational facility outside of Calgary. So a water supply, but also now, admittedly, we have to treat it because we have human and other activities on that surface. A fellow that sent me this picture worked in Fort McMurray in Alberta, northern Alberta, and huge, massive wildfires back in 2016, evacuated the whole town, millions and millions of dollars in damage. And of course, the firefighting itself, the retardant that was used and so on, affected the water supplies. I mean, the biggest effect was the fact that the water treatment plant itself was partially damaged in the fires. So obviously we have to build the structure around of these reservoirs and impoundment structures to make sure that they function the way we want them to. And that's based on the characteristics of the feature itself, its depth, its width, its does it freeze? You know, where are the natural sediment areas happening, its temperature, and so on, and we build accordingly to protect that. Here's a cutaway. It was similar to the one in the video, basically where, you know, we impound water, but we still have to remove silt. We still have to deal with high water, unseasonal or otherwise. Some of you might have seen on the news, YouTube has some of the videos as well of that dam that was damaged or blown away up in northern India and the Himalayas. when a piece of glacier basically broke off and flooded this very steep valley with a dam on it. And the weight of the broken up glacier and the muddy, damaged water wiped out the dam and, of course, downstream. I think 150 people are still missing or dead. So, you know, there's always risks around impounding those volumes of water. And if you like Dwayne "The Rock" Johnson, just watch San Andreas, you know, where he's, you know, the superhero guy that protects Los Angeles after the dam breaks because of an earthquake. So, you know, these are man-made structures and engineered and designed, but they are, again, still subject to other impacts and, you know, maintenance required. So a storage tank, there's typical above ground steel water storage facility. So just by looking at its shape, you can see, okay, it's more for volume, perhaps firefighting or seasonal droughts, that sort of thing, as opposed to energy. But I mean, that would still provide a ton of extra hydraulic pressure, you know, in the system that it was built in. But remember, when we build storage, and this is, you know, where the size, how much storage do we need? We're doing it because we have certain considerations that we have to meet in our systems. And it doesn't matter whether there's 50 people in the community or 5 million. Their usage patterns for drinking water change seasonally and diurnally, right, over the course of a 24-hour period. So if all 50 people want to use water at the same time on a cold day, okay, our system might be able to handle that. But what if it's the hottest day of the year? It has to handle that too. And by the way, everyone's got a garden. We need to handle that. And there may be a fire. So how much water will we need in that case? So all of these are added on factors for saying if we think we need 100 liters of storage, okay, but because of the peak, right, it's not average over a day. No one uses the average amount of water, right? Well, maybe you do once a day, but our average flow might be 100 liters a day. But in peak, it might be 300 liters. Well, we don't want the pipes to run dry. And a lot of systems around the world face that because of growth, population growth, or lack of capacity, carrying capacity of the pipe due to age and corrosion, things like that, or leakage, water loss. You know, again, that example, if we originally had 100 liters being produced out of our treatment plant, but only 50 liters are making it, well, now we have to build that in. There's a famous example in this part of the world of a small community on Vancouver Island about 20 years ago, had a storage facility built, about 300 people living there. And the storage facility was a little removed from the town because they built it on an elevated part of ground, and they pumped in from a well to fill the storage facility. And then the grade, this water main that went through kind of a wilderness area, swampy and muskeg and so on, eventually get to the town. And they were losing so much. The pump was always running. And when we talk about pumps and motors and how that works, the idea is we pump to storage, the pumps can shut off and save us some energy, and then the storage facility will provide that. Well, this community, the pumps were never turning off and they couldn't keep the reservoir full. So they said, something's going on. They checked the pipe, they couldn't find any leaks, they checked the inside. So we're gonna build another tank. There's just maybe more people living here, so we'll build another tank and another pump. And so they did that. What was interesting is when they switched over to the new pump and tank so that they could do some maintenance on the old pump and tank, they found the pump never ran. The reservoir filled up and it hardly emptied. They checked the valves, what's going on? No one was out of water. And then the big swampy, muskeggy area between the reservoir and the town all dried up. And what they realized is, we didn't know it, but either through the bottom of the reservoir, the tank, or through the pipe, they had this monster leak that no one could find. And so instead of delivering that water to their customers, they were actually just delivering it to the environment. So paying to pump water, disinfect it out of the well to a tank, and then it was just draining into the ground and created this swamp. So this swamp that a lot of people had always known to be there 25, 30 years vanished, dried up. So now they have 2 tanks and 2 pumps and hardly any demand, which can create other problems. But we have to build our facilities, our storage, to suit what we need it to do for us. And every community is a little different. We have to satisfy emergencies. We don't want there to be an emergency, and that could be a fire, could be a drought, right? It could be a major earthquake or contamination event where all of a sudden the half the water system is shut down. Okay, well, how do we provide enough water? When there were forest fires, wildfires in BC a few years ago, a lot of the surface water systems, there were real concerns because of the firefighting activities, planes dropping retardant onto the fire, and of course it runs into the surface water supply. So they had to test and treat for that to make sure that water was still safe for their communities. And of course, as operators of a water system, which system, which seasons, which days, weeks, days of the week, or which months are the best, where you have a lot of water and or potentially your system is stressed. Cape Town was very famous. I think I might have mentioned that a few years ago, they expected to completely run out of their reservoir system, mostly because of leaky pipes. And they pushed hard to find those leaks and look at how their system was being run. And the result, a year later, was that they were able to defer that 0 day where they were running out of water. But storage does these things for us in our system: satisfy the peak demands, satisfy emergencies, and handle those seasonal changes. In Victoria, the surface water supply originally was built to provide about 6 billion liters of storage. And they raised the dam 2 meters, just built on top of the existing dam, cleared the edges of vegetation of the lake, and now it provides 11 billion liters to deal with population growth, mostly, and to deal with emergencies, the concern that with climate change, they were noticing fewer and fewer days of substantial rain. So it meant that the need was there to put more water into storage. Now it's raw water, it still needs to be treated, but it's there, and it's a surface water supply, so there's no wells or pumps or anything. It's then gravity fed into the treatment plant. So it's about planning for what your community needs. And of course, a lot of systems, the amount of available storage and water means that's the only service we can provide. So councils will actually say no to certain developments because the engineers have said, we can't have that development in our city, not because we don't want it, but because there's not enough water. So storage is really critical around figuring out how much to need, how do we need, and building that for the future. We talked a little bit about types of storage that are available, and they may ask you on the exam the difference between a primary storage or secondary storage, right? And primary storage is like the Hoover Dam there. The water that's impounded behind that dam is what we would call primary storage. It's raw water. You can't drink it through a municipal system without treating it first or disinfecting it. Whereas secondary storage would be water that is piped from this dam and pumped into a disinfection facility or treatment facility and then delivered into the community. And that becomes secondary storage. Could be, we've seen examples earlier of the elevated tank, clear well, hydrodynamic tank, and some of them are very small. It can be, secondary storage can be for just one house. If they have a little well supply, pumps into a hydrodynamic tank and just supplies what that house needs for a day or two. And then the pump turns back on, pulls more water from the well, fills the tank, and that supplies the needs for that single family. That's secondary storage. There's an example. All through the United States, storage and prairies where there is no elevation, this is a good example of an elevated storage tank that does both, right? It provides storage, i.e. enough water, but it also provides the elevation that's needed to push the water through the system. Otherwise, yeah, the grade line would crash and there'd be no water available. Right? A couple of cutaways of ground water storage. It can also work for surface water supplies as well. And remember, they're sized according to what the community itself needs. And, you know, big is good, but too big is not so great, because if you have storage facilities that never empty, and we'll talk about this more in operations and maintenance, but, you know, now the water goes stagnant. The American Water Works Association has said that, based on studies it's done on water quality, that, you know, you really don't want water sitting in a reservoir for more than a week. And that, you know, if you can get 30% turnover in a day, great. But if you can't, every 3 days. So too big means that you never move that water out. And so then you get bacteriological regrowth. So we're not talking about the water quality aspect of it today so much, but just the difference between, you know, primary storage like this and the secondary storage like that, right? A couple of other examples. And remember, an elevated tank is, you know, your first clue, because it's elevated, all right, we're also providing energy, right? That's the hydraulic component coming in. And some of the hydropneumatic or pressure tanks can be very small, that basically pull water out of a clear well, which may be used just simply to remove sediment or provide a little contact time. If we're adding chlorine, a clear well can be where that water sits so that it has sufficient time before it gets moved into the system. All right, so before we get into the types of storage, I've got another little video, if I can get it to work. So let's do that on storage itself. Okay, just a very short video.
Urban areas usually get our water from some kind of centralized public system. Operating a water system is a major responsibility that has implications for public health and safety. In dense urban areas, a clean and abundant supply of water is an absolute necessity, not just for drinking, but also for sanitation and firefighting. And it's not just something we need every so often. Water is a constant necessity, both day and night, on weekends, holidays, and any time in between. So the job of finding enough water, making it safe to use, and then reliably distributing it to the system customers with almost no downtime is a monumental task that requires a lot of infrastructure. And probably the most visible component of a public water system is the elevated storage tank, also known as a water tower. I'm Grady, and this is Public Works, my video series on infrastructure and the human-made world around us. This video is sponsored by Bombas. More on that later. Let's say you're the owner of a public water system. You found a source of water of sufficient quantity for your customers. You found a way to clean that water so it's safe for them to use. And now it's time to send the water on its way. There are a few ways we can get water from one place to another. One of them is just to carry it there. Whether it's on the back of an animal, or on a truck, or a bottle in your backpack, we still physically carry water all the time. But it's usually not the most efficient way. The first infrastructure dedicated to water conveyance was the open channel. Whether in a ditch, canal, or aqueduct, the water is carried by gravity, sometimes over very long distances. We still use open channels to carry water for irrigation and drainage, but they have some disadvantages as well. The water is exposed to pollution and contamination, channels bisect the land, making it difficult to get across, and the water can only flow to areas of lower elevation than where it started. And that last one's a big disadvantage, especially if you're trying to deliver water to an area with hills or mountains. So most public water systems today rely on pipes for distribution. Simply putting a top on an open channel allows us to take advantage of pressure to move fluids where we want them to go. Just like electrons in a wire flow from high voltage to low voltage, a fluid in a pipe will flow from high pressure to low pressure. So if you raise the pressure at one end of a pipe, you can send your clean water to anywhere you want it to go. And how do you raise the pressure of water? With a pump. A pump is a device that moves fluids. In some cases, a pump literally lifts the fluid to a higher elevation, but in most cases, a pump imparts energy to a fluid by raising its pressure. And pumps, especially the size of pumps that serve entire cities, are expensive. So if you're tasked with choosing the size of pump that you need for your public water system, what do? Maybe you measure the amount of water that a city uses in a given day and select a pump that can match that flow rate. Let's see how that would work. It's midnight in your city and most of your water customers are asleep. Besides the industrial customers that run 24/7, water demands are minimal, and your pump is having no trouble meeting them. But around 5 a.m., automated sprinkler systems start kicking in. Around 6 a.m., people start waking up, taking showers, brushing their teeth, cooking breakfast, all things that require water. And it doesn't take long before the water demand exceeds the capacity of your pump. Almost right off the bat, your new pump can't meet your system demand because it was only sized for the average. Water demand in large urban areas can vary significantly over the course of a normal day, with the peak hourly demand, usually in the morning or evening, sometimes being as much as 5 times the average daily demand. So if you're trying to meet your customers' water needs using just pumps, instead of just one, you might need as many as 5 pumps, or one huge pump that can do the work of 5. And not only that, you'll have to be constantly cycling the pumps on and off to meet the variable demand, increasing the wear and tear on your equipment. And here's where storage comes in. Let's add a water tower to the system and try this experiment again. It's midnight and demand is low, but your pump is running full wide open. Instead of water flowing to customers, it's flowing into your water tower, filling the tank slowly but surely. As morning comes and demand starts to increase, your pump continues running. It's not able to meet the demand on its own, but the stored water in the tank is making up the difference. All your customers are getting the water they need. As people start their day, demand again drops below average, but the pump keeps running and the extra flow goes into the tank. Demand again begins to spike as residents of the city start cooking dinner, taking baths, and watering the plants. All this extra water use drains the tank again before most people go to bed and the cycle starts again. It's pretty easy to see how storage makes your water system more efficient. It smooths out the peaks and valleys of water demand, not just on your pumps, but all your upstream infrastructure, including your water treatment plant and raw water supply. Without storage, all those facilities would need to be sized for peak demand, increasing their cost. With enough storage, pumps and other infrastructure can be sized for average demands, saving not only cost but also complexity, because you don't have to predict changes in demand and respond accordingly. Sometimes those peaks and valleys are predictable, but sometimes they're not. Some of the biggest water demands in urban areas are from fires. Without a firefighting force and enough water to supply them, fires can burn out of control in dense urban areas. In fact, many of the deadliest disasters in history were fires in cities before modern water systems. Now most municipalities and building codes have minimum requirements for the amount of water that must be available to firefighters. And having water stored and ready, like in a water tower, goes a long way to being able to respond to an emergency. You may be thinking, come on Grady, this is nothing new. Storage is the age-old solution to any situation where supply doesn't match the demand. And yeah, it might not be anything remarkable to store water in a big tank, but water towers aren't just big tanks. They're big tanks elevated above the ground. And that's because water towers aren't just storing water, they're also storing energy. Water distribution systems rely on pressure to get water where it's going. If you've ever taken a shower with low water pressure, you know how frustrating it can be, because you can't get enough water out of the tap. Pressurizing a water system is also important for public health. Without enough pressure in the pipes, contaminants could make their way into the system through taps or small leaks. Most water systems get their pressure from pumps, and it takes a lot of energy to maintain this pressure. So having the ability to store not only the water itself, but also the energy that's been imparted to it by pumps is important. In some areas where electricity costs vary based on demand, you can run the pumps at night when electricity is cheap to fill up your water tower, then leave the pumps off during the day when the electricity is more expensive, allowing just the tower to pressurize the system and serve your customers. Storing energy this way is also carried out at a larger scale to help with electrical grid reliability, but that's a topic for another video. Elevated storage is also beneficial during a power outage by keeping the system pressurized even when the pumps are out of service. But how elevated do they need to be? You might know that pressure within a body of water is related to the depth. The deeper you go, the greater the pressure. Just like in a pool or the ocean, a water distribution system has this same relationship between depth and pressure. It just happens to be confined within a series of pipes. So you can imagine a water distribution system as a virtual ocean under which we all live, and the water surface in elevated storage tanks represents the surface of the virtual ocean. Imagining a water system this way makes it easy to see the challenge of delivering water to customers at the right pressure. If our cities were flat, this would be pretty simple. All the buildings would sit at the same depth in the virtual ocean. But most areas have at least some amount of topographic relief. Customers at low elevations are at the bottom of the virtual ocean, where pressures can be too high. You might think this is a good thing, but plumbing pipes and appliances are only rated to certain pressures, so exceeding those ratings can cause serious damage. Sometimes buildings at low elevations will be equipped with special valves to reduce the pressure. Customers at high elevations will be near the surface of the virtual ocean, having very low water pressure. As I mentioned, this can be not only frustrating, but also lead to contamination of the system. To solve this challenge, many large cities maintain separate distribution systems called pressure zones, each with their own water tower, to serve customers at different elevations within the city. But what happens if you need to serve customers at different elevations in the same location? Tall buildings like skyscrapers can have adequate water pressure on the lower floors, while the higher floors can go up near the surface or even above the virtual ocean in the water distribution system. So instead of relying on city water pressure, most tall buildings use their own pumps to provide water to the upper floors. And some cities like New York even require that each building have its own elevated storage tank. Not every city uses water towers. Some have their entire water supply at a higher elevation, minimizing the need to add pressure to the system. And sometimes it just makes more sense to rely on pumps alone to keep the system up and running. After all, water towers aren't cheap. They take up quite a bit of space, and they can allow water to stagnate if it isn't circulated enough. But with public water supplies, reliability is key, and it's been a long time since gravity was knocked offline from a thunderstorm, so elevated storage tanks, in some form or fashion, are definitely here to stay. Thank you for watching, and let me know what you think.
All right, so I like the video for a couple of reasons. It basically talks to the hydraulics, which are critical, because without the hydraulic considerations of the system, it makes it very difficult to plan for providing enough storage. And also, every system is going to be a little different as to what it needs in terms of daily peak demand versus low seasonal demand. And so we try to balance the volume of water, its quality, based on that cycle, not just a 24-hour cycle, but the whole calendar year. And you'll have in your system the same considerations as to when is water needed, for what purposes, and so you get a sense of what are those volumes that you need to treat and deliver to the customer. All right, let's go back to our PowerPoint. Okay. First, I have to share the screen, don't I? All right, so we'll talk a little bit about the actual, and here's a couple of examples. So this is Vancouver, one of the reservoirs that's impounded with a dam, and this is a closed watershed. This is an above ground steel tank for a small community, and they're about to go in and actually clean it. You can actually see a lot of the storage facilities, small ones. The best way is to have an outside gauge that tells you how much volume is in the reservoir at the time. Of course, our remote SCADA systems can do that too. So obviously, when we build one of these storage facilities, we have to maintain it so that, you know, especially we're talking secondary storage here. So this is water that's already been treated. So remember, in the disinfection discussion, we're talking about that finished water now available. So just as the pipe itself is, most of the time buried and out of sight, out of mind for people, it's as long as there's positive pressure in the system, we can't usually have contamination unless we have a backflow or back pressure event. But a facility is the same. It needs to be inspected regularly to make sure that hatches aren't opened up, that people can get in or out of the facility, either to do something to the water itself or to create a leak, to do something that would then put that reservoir offline. Happens all the time in North America. The American Water Works Association has very robust standards for both treating the facility, but also for protecting the facility from vandalism. And there's always been a bit of an argument for smaller facilities, or a debate, it's not an argument. Is it better to have a facility in a remote area where there's nobody around? Because then you don't have vandalism regularly, because people have to go a long way out of their way. Or is it better to have the facility right in plain sight? City of Vancouver has a large reservoir, concrete finished water reservoir, that it's got tennis courts on top of it. So the idea is that, it's right in the middle of where people are. And as long as those hatches are closed and they have a SCADA system on it, the chance of someone doing something intentional is pretty rare or slight. The vandalism, when you got a lot of people around, not likely to happen. Whereas in a remote area, there's nobody around. Okay, could do that. I can hear someone. Make sure you're muted, please. Anyway, one of the other concerns about I'm just going to ask Denver to.
Orange.
Oh man, I don't know why this person does that. Sorry about that.
No worries. Hopefully all is good there. So one of the concerns about having storage facilities is that they're protected. And because they're finished water supplies, you really do need to ensure that you have a regular, an operator has been tasked with visiting the site regularly, painting it to protect against rust, and there are standards for the right kind of paint to be used and how to test that reservoir before it's put back in service. Vandalism is often the one of the key areas to worry about, because a lot of times people are curious. They want to know what's happening. A sign saying drinking water facility may or not keep people away. So whether that's a locked gate, or whether it's a hatch that's locked, or a ladder that's been removed so people can't climb up on them. In this part of the world, it's quite common for elevated storage tanks to attract mostly young people, but people to want to explore them and hang around on them, paint them, vandalize them, that sort of thing. So, it's a good sign of a system that's, being efficient in its maintenance if it can have a program to minimize the chances of that happening. There have been a couple of notable times when facilities were broken into. One on the island here about 15, maybe 20 years ago, and they had to shut off the intake for the whole water system because someone broke into the building, and there was a pipe system into a reservoir and dumped some material into the reservoir. It turned out that it wasn't a toxic material, but it took 3 days to get the samples back. So in that time period, an entire community of 10,000 people had no water. They basically said, because we don't know what that is, we can't let you use it. So that means not just boil it, use it at all. So the hockey rink got taken over, and the city brought in truckload after truckload of bottled water, the big 25-liter bottles for people to use. And it's not uncommon that in a contamination event or a potential contamination event in a storage facility means that the system has to, the operators of the system have to find another way of protecting the system and providing water to customers. So that was over $1 million that the city spent to protect, the people that were, their customers, because they just couldn't take the chance. So the storage facility can be a potential cause of contamination. Sometimes, if a reservoir is too small, what happens is the water level rises, but it's constantly back and forth between a pump cycle, and that band of elevation around the reservoir wall can be a bacterial breeding ground and becomes more of a problem because over time, bacteria can grow on that reservoir. The other problem, if the reservoir is too big and doesn't turn over, sometimes the water gets too old. And so, in a fire, no one cares, right? We're putting the fire out. But when there aren't very many fires, some communities will never see a firefighting event, but they've still sized the reservoir, the storage tank, for that potential happening. So they have to do something. Sometimes they dump the water. Sometimes they pull the water into the system, and they'll do other maintenance with that water, like flushing a water main. And they'll actually pull the reservoir down artificially by opening up fire hydrants, clean the water mains, allows the pump or the treatment plant or the well to supply more water into storage. And now that water is fresher, younger, so that we don't have the stagnation happening. So one way to know what's happening in your system is to take a sample. And when we talk about water sampling in the days ahead, part of it is to know that your system is compliant with regulations around the actual bacteriological health of the water system. So the reservoir, a finished secondary storage, right, not primary, but secondary storage facilities are part of the water distribution system. They have to be protected the same way a pipe or a valve or a service line is protected, right? So we talked a little bit about inspections and the need to do them. So depending on the resources of your system, and of course, depending on how many storage facilities you have. The video talked about, with elevation change, splitting the city up into multiple pressure zones, each supplied with its own reservoir. And I've worked in a couple of those. And so you have different size reservoirs where the water only circulates in a subzone or a pressure zone, but it still needs to be inspected. So now you've got 6, 7, 8, 10 reservoirs in a city, and the neighboring city has none because they don't need them because of elevation and the size of the pipe. So now their resources are totally differently allocated. So City of Victoria, no reservoirs, great residuals, great bacteriological health. Next door, community of 100,000 people, similar to Victoria, 100,000 people, has 14 reservoirs because of the topography and the need otherwise to provide adequate water at adequate pressure. Well, so now there are 3 people looking after reservoirs where the City of Victoria doesn't have to spend a dime on reservoirs. So every system is different, but you have to treat that reservoir like it is part of the distribution system. It is, right? So you need to disinfect, you need to test it, sample it, identify any defects. So your inspection program is a little different than it would be for a system that has only pipes and hydrants and valves. And of course, periodically clean a reservoir. American Water Works Association talks about every 5 years, depending on the quality of the water going in, of actually emptying the reservoir and cleaning it out. Because it is part of the system, it does need to be vented to prevent vacuum, but also when the reservoir is filling, to make sure that air that is displaced as the pump fills the reservoir is removed, right? So you'll see an overflow on the side here, and also a vent. This is a close-up of the vent. You can see the screen to keep the birds out, but the number of vents and their size will be designed by the engineer and or the pump and reservoir supplier to make sure that you don't overpressurize the reservoir or create a vacuum either way, either in filling or emptying. And that means that if your reservoir is ground level, that those vents don't get grown over as well. The city of White Rock, not far from downtown Vancouver, has one very large concrete reservoir, finished reservoir. And because of where they took their water from, they didn't disinfect. They didn't feel like they needed to, and their water quality samples bore that out. However, the concrete started to break around one of the vents, so it was a square reservoir, and birds got in and nested on some of the pipe rack that was over top of the water. And you know, if a bird sits still long enough, you know what it's going to do. So all of a sudden, the city had E. coli samples showing up, contamination, bacteriological contamination. And because they weren't disinfecting with chlorine, there was no residual to actually meet that demand of bacteria. So they had, again, to shut down the water system and find the problem. And a lot of it was just age, but they hadn't inspected often enough because of what could go wrong, right? The reservoir's been there for 25 years and nothing's ever gone wrong. Well, it's the same as if you don't fix your fence after 25 years, it'll fall down all by itself. So for a water system and for operators, they really need to be aware of what those potential risks are and where those effects of age, you don't want it to be neglect, right? You want to have a regular program of inspection. Here's a couple of pictures of divers actually inside tanks using vacuum cleaners that are connected to pumps outside the reservoir and are actually cleaning out the reservoir from the inside. And that may be because the reservoir is too important for either energy level, right, height, or volume, time of year, so they have to do it live. You'll see a lot of modern, you may have them yourself, the newer reservoirs will be broken into two cells so that one cell can be taken out of service while the other cell is still in service.
I can't remember.
So anyway, that's one.
Huh? Hey.
Hey, Shannon.
Huh?
There he is. Well done, Shannon. Okay, so remember, when we're dealing with storage, we're dealing with part of the live distribution system. So your policies around cleaning the tank will vary based on what the tank is made out of, the quality of the water that goes in, that sort of thing. So if you take the reservoir out of service, you can drain the water. Usually, to save water, cities will actually drain the water and then do other things with it, like flushing or scouring other pipelines. But it needs to be disinfected before putting back into service. You won't have to do this on the exam, but just know that the American Water Works Association has disinfection procedures for reservoirs just like they do for pipe. And remember, with disinfection and chlorine, the higher the concentration, the shorter the contact time. So this standard one is basically filling 5% of the tank at 50 milligrams per liter or parts per million, waiting 6 hours, and then don't dump the water, fill the tank. And if you've done your math right, 5% of the volume taking 50 ppm, when you add more water, without adding more chlorine, it dilutes so that when the tank is completely full, it's got about 2 to 2.5 ppm or milligrams per liter. Now you can wait for 24 hours. And think about it this way. You've got a steel tank. You've been inside the tank, brushing it down or using a pressure washer on it, or just sweeping out the bottom of the tank. Some utilities, they just go in there with a shovel and a broom and remove the sediment. But the extra chlorine on the bottom 5% of storage allows for a very detailed, intense clean in that 6 hours. And then when it fills, you have the regular 2.5 ppm for the vault for making contact with the rest of the walls. And then you can sample it. You don't have to drain it again, but you can actually test for a bacteria and wait for those samples to come back, and then put the system back live in service. The other option is that you do a much stronger dosage of 200 parts per million, spray all of those surfaces on the inside, taking all the safety precautions, of course. Now you only need to let it stand 30 minutes. It's just soaking all the exposed surfaces. That's ladders and inlet pipes and any manifolds that might be in there, and the walls and the floor. Wash them, and then after 30 minutes, purge it, drain it, and now you can fill. But in both cases, you do need to sample, right? You can't put any part of the distribution system back into service without sampling first. The other thing you may do, depending on the size of the reservoir and how often it turns over, is in your system, set it up for regular sampling. So it could be weekly or monthly, depending on the size of the reservoir. And, you know, provided that you've blocked or off, you know, cracks, and you have proper locks on your hatches, and you do the cleaning once every 5 years, 3 to 5 years, depending on the water quality. Now you have a check, maybe every 3 months, every month, depending on your water quality, to know that the reservoir is safe. The other thing about a steel tank especially is they corrode. So the AWWA will talk about the right types of coatings. So you always have the ability to find a supplier that can deliver not just house paint or fence paint, but the right paint for that surface, so that you minimize the corrosion. And in this part of the world, the water quality is good, but it is quite corrosive. So there needs to be some sort of coating to prevent that oxidation, right? That oxidizing of the exposed steel on the water supply. So many different options, but again, in your system, know that. We'll talk a little bit more about cathodic protection, that's down in the middle bullet here, the way of protecting the metal, either on a valve or a service connection or the main itself, by basically sacrificing another metal, typically zinc or magnesium, so that it'll get corroded before your pipe or your reservoir, right? So that's another way of doing it. The most common is just paint it. Use the proper paint, and then inspect it from time to time to make sure that that paint is in good condition. Freezing could be a potential issue, probably not in your part of the world. This part of the world, for sure. And that's typically in the level controls, in the hatches, and the metal assemblies. And so it's really important that again, that reservoir be inspected regularly. Here's an example of a primary storage. I don't know, you can see that video. You see the spots on the walls of the video, or on the dam. That's pretty steep. They're actually goats. They actually climb up there to eat the moss off the walls. Not necessarily a water quality concern at that side of the dam, but you know, not what most operators would consider that they have to deal with. The European ibex, they're good climbers, obviously. All right. So that video that I showed you really talks about building storage based on what your system needs and determining the demand over a 24-hour period, seasonally, and based on the population. Of course, our cities tend to grow, our towns grow. You know, in your area and parts of BC, where there are lots of people coming at certain times of the year for recreation and tourism, the water system has to be built for that, even though those people don't live and pay taxes there. But they show up for a while, 2 weeks or a month or 10 days, and use a lot of water. So we still have to size our system accordingly, and storage can help with that. So we're really looking at, you know, properly maintaining our system for all of those aspects. Which of the following best describes a primary water storage facility? Well, out of the 4 choices there, a dam. And that may show up on the exam. which of the following is not considered to be a phase of the water cycle? So out of that, well, we talked about transpiration and evaporation. We talked about surface runoff. So we're looking at retention. Now let's talk a little bit in the time we have left, and I will send you this file. I was looking at my chat file capability. I don't know, it's not letting me send a file, so I might have to send it to Ignatius. I'll try a couple again, but just to make sure, I'm going to send you this PowerPoint. But as far as groundwater is concerned, we talked in the video about an aquifer, right? Is the sand that holds the water. The other thing you need to know for the exam is that the water table is actually the top level of that groundwater. And when that top level of the groundwater comes higher than the ground surface and is under pressure, we call that an artesian flow, right? And that's just based on the configuration of the groundwater and the elevation itself. So here's an example. We saw that in the video. So the watershed, you know, water comes from the sky as precipitation, percolates down into the ground. The igneous rock on the bottom prevents any water from moving below. Water always moves towards the low elevation. And basically an influent stream is one that contributes to groundwater. The effluent stream on this side is actually picking up water from the unconfined aquifer and taking groundwater and turning it into surface water. And that's basically where our groundwater exists. And of course, some of it can be, you know, hundreds of feet deep. Others, it might be only inches below the surface, depending on where you are in the world and what's happening. In Florida, for instance, in the southern United States, very flat, a lot of elevation, low elevation, almost at sea level, and limestone underneath, above a lot of the aquifers. And as the aquifers have been pulled out through pumping, it actually creates a hollow, and the limestone collapses and you have a sinkhole. Every year there's a story out of Florida of a house being swallowed up because of a sinkhole created. And it's typically because water is being removed by wells, and that creates the void. But in most parts of the world, the ground itself that is suitable for an aquifer doesn't collapse when water is removed. And it's based on the type of rock and soil, the porosity, which is the size of the pores, could be sand, silica, topsoil, etc. The characteristic, as it says, the permeability of the soil and rock is what allows the aquifer to either be, you know, exploited by us or used, or if it's something that we have to develop further before we can take water out of it. Here's a cutaway of a groundwater system with different types of soil. This is the expanded view, the exploded view. So we have vegetation, topsoil, water moves through and creates a groundwater aquifer. So obviously we search for these if we need to use the water supply. What we want as a suitable aquifer is that there's sufficient enough volume to do what we need it to do, that it's permeable. In other words, water can move through it. And that may be on the exam, just to be able to define permeability. And that when we take water out, it can be refilled or recharged, right? The recharge area is where that water, you know, lands and moves through the ground to recreate and replenish the aquifer. And of course, we then determine what the yield is on our well. We actually drill it and then start pumping water out. And then when we turn the pump off, how quickly does that area recover? So these are the key areas, right? Volume is sufficient, permeability, and that it's recharged. Because if you have to go to the expense of drilling a well once and then the water's gone, then not a good return. Again, a cutaway that we saw on the video, surface water, permeable through the soil into between the clay. So the clay would be impermeable. And here's our recharge area of an aquifer. So be comfortable defining, you know, the permeability, a recharge area, and an aquifer. So we want to know, you know, basically when we're looking at groundwater as a supply, okay, the interesting thing is because it's being filtered, it's typically bacteriologically safer than surface water because the soil and particulates themselves have removed some of the microorganisms if there's a deep enough aquifer to do that. If there's not, if the groundwater is the well and the aquifer is filled up so quickly by surface water, that becomes something we could define under our regulations as GUDI, as groundwater under direct influence, which means that it may have bacteria. A lot of deep wells, that's not the issue. The issue might be things like magnesium or manganese or copper or iron, but not bacteria. Well, if we have shallow wells, it's possible that they are acting really like, whoops, that's the last slide, surface water. And that may or may not be a good thing. So we want to make sure that we treat our well supplies in that fashion. I wanted to share with you your homework. So let me see if I can find that, and we can just finish up the last 10 minutes with that. That way you get a head start. Let's see. So those were the highlights of that. Here's the homework that I wanted you to take with you. So I'm going to try and figure out how I can get that to you because it's not letting me send a file. So I'll try and figure that out. Otherwise, I can email it to you. In the meantime, these are the questions that we want to look at based on today. And actually some of the disinfection stuff that we talked about. Remember last week when you were doing disinfection, it's important to remember, especially with chlorine, that not only are you destroying pathogens, and of course pathogens are the disease-causing organisms in our water supply, but it's also, we may not destroy and remove them. The other word we're looking for here is inactivation, right? We want to inactivate them. And that's important because disinfection doesn't always kill all the bugs, right? But if it inactivates them, it means they cannot reproduce in our guts and make us sick. What does the presence of total coliform in drinking water indicate? Well, probably refers back to this word here, right? Pathogens, potential pathogens in the drinking water. Doesn't mean that we're going to get sick, but we need to sample for it to confirm. All right, so think about your own system, the treated water system, and where would you take samples from? Well, they need to be taken from places where people are actually using the water. So that could be it could be a reservoir, it could be at the outlet side of a well, or it could be in a block that could be a randomized sample or a representative sample of what our water system is like. So in a well, so this is the water table question. So these math, we talked about that a little bit before. Static water level is 25 meters below the surface, and the pumping water level is 47. What is the drawdown? So I'm not going to give you the answer, but think about a cutaway view of a well with the water table at 25 meters and the pumping level at 47 meters. It'll be the difference between the two. So I kind of did give you the answer. So in a well supply, a static water level, pumping water level, plus the drawdown, static water level, pumping water level, plus the drawdown equals, we're looking here, basic yield, right? How much comes out of the well. GUDI, we've just talked about in the slideshow, groundwater under direct influence. What units is turbidity measured in? We talked about that during the treatment and disinfection, right? So make sure you're comfortable with that. You don't have to necessarily spell it out, but definitely know what the the initials are, right? The NTUs. Primary water storage, we just talked about today, 2 examples. And we're going to talk some more about water sampling. And when we're doing bacteriological samples, we put sodium thiosulfate in the bottle for a specific reason. I know you know this, so we'll let you figure that out. And then, of course, what's an aquifer? So those are the sample questions. Next week, we're going to talk a little bit about, after we talk about water sources, we're going into the actual operation and maintenance of the system. So we're going to spend a couple of weeks looking at that before we get into pumps and motors. And we may end up talking a little bit about, I'll talk to Ignatius first about that, how much of the safety stuff. We can talk about the types of safety questions that are on the exam, but really it's we want to make sure it's relevant for you. All right, so that's actually it for today. That's the module. So let me try and figure out how I can send you these files, because if it's not letting me send it, then that doesn't work. I'll have to send it by email. Yeah, normally I end up with a file list here that allows me to, no, I don't have it. So I won't be able to send you the files. I'll email them to Ignatius so that you can have them. But what it is I've just turned the PowerPoint into a PDF for you. So, hello.
Yeah, you'll send that to me, really.
Oh, did I? Okay, even better. I don't know if I sent you the PDF. It might be the whole PowerPoint, but whatever.
Yeah, just send it via email and I'll take it.
Okay, I'll do that. And I think basically we're done for the day.
Okay.
So I will send you that stuff, Ignatius, and then later in the week, I'll send you the prep for the for next week's session.
Okay.
All right. Thanks very much, everyone. We will see you next week.